All right. Thank you, Mark. And let me start by thanking the organizers for giving me and giving us the opportunity to present our recent work on quantum gravity contributions to the gauge and Yukawa couplings in proper time. This is a work in collaboration with Gabriele Giacometti and Dario Zappalà from University of Catania and with Camilla Kowalska and Enrico Sessolo from NCVJ in Warsaw, where I did my PhD. And I was actually still in the final part of my PhD when we started this project. And now I moved to KBFI in Tallinn, in Estonia. Let me start with a quick outline of this talk. So I will start with proper time renormalization group flow equation, a very quick introduction. Then I will quickly as well discuss asymptotic safety in quantum gravity. I'll then go to the main part, so what the paper is about, so contribution from quantum gravity to the running of gauge and Yukawa couplings. And finally, I will discuss phenomenological implications of the results obtained in the paper. So let's start with proper time flow equation. So here you have it. On the left-hand side, you have scale derivative of a Wilsonian action. And on the right-hand side, you have the exponential of the Hessian integrated in this S variable that we call Schwinger proper time. And then you have the derivative of some regulating function, f of k. Now, this flow equation is derived by, or is obtained by taking the one loop effective action and using the so-called Schwinger proper time representation, in which you replace the log with this integral of an exponential. And of course, we need to, I mean, as long as we are here, we are not yet regularized, so we need to introduce a regulator, like I've done up here. And usually common choices of this regulating function is a combination of incomplete gamma function parameterized with an integer number m, which needs to be bigger than d over 2. So in d equal 4, m starts from 3, 4, 5, and then gets up to infinity. And actually, infinity is a special limit I want to take into consideration here. So if I take the limit for m going to infinity of this regulating function, then I get Heaviside theta. And once you put this inside your flow equation, you obtain a Dirac delta, which picks your integral at 1 over k squared. And basically, the right-hand side of the flow equation simply becomes the trace of the exponential of the Hessian over k squared. So you obtained a very simple form for the right-hand side of the proper time flow equation in what we call sharp cutoff regulator. So first of all, let me comment on the fact that this is a sharp cutoff in S, and S is energy 2 minus 2, while sometimes we are used to think of sharp cutoff as a sharp cutoff in momenta. So in a way, this is a sharp cutoff in 1 over momenta. So this is somewhat important. Also, let me comment on some literature. So there is a result, or at least a claim by the Alvis from 2018, who says that the Wilsonian proper time with sharp cutoff, so with this one, is exact and gauge invariant. However, this goes a little bit in contradiction with a previous work by Jan and Daniel, who in 2002 showed that the proper time version of the effective average action does not reproduce the correct two-loop diagrammatics. Now, what I mean by two-loop diagrammatics here, so what they did, basically, they took the flow equation in proper time, they used a loop expansion and computed the two-loop effective action. And what they obtain when they look at the diagrammatic version of this is the correct result that you would expect from the ERG, plus some extra contributions, which are non-local, and therefore make I mean, this having extra contribution with respect to the ERG result makes the result, so the two-loop action in proper time flow basically not correct. However, you might still wonder if there is any part of this two-loop diagrammatic result that can be saved, or if you want that is correct. And this is where we started and eventually published last year a work with Gabriele and Dario, on the perturbative expansion and proper time flow. And what we did, we showed, starting from the scalar ON theory, that two-loop beta function and anomalous dimension are correct. So basically, when it comes to the purely local part, so here the one loop and the local part of the two loop, we see that this is correct, which is basically in agreement with what they have found in 2002. But also, and more surprisingly, we find that the first non-trivial contribution to the wave function normalization, so the anomalous dimension, is also correct. So the first, if you want, non-trivial, non-local part of the diagram is correct. And this is quite remarkable. Even more importantly, what we did, we studied the SUN Yang-Mills theory, and we obtained that even in this case, the two-loop beta function can be recovered in proper time flow equation. We used background gauge fixing, so in a way, we are able to exchange beta function with anomalous dimensions, and here we did it directly from the anomalous dimension. But the important part is that we were able to compute and obtain directly from the flow equation this minus 34/3. Now, importantly, this can be computed even in FRG, it can be obtained even in FRG, but in FRG, the way to do it, because you have a regulator, is to impose word identities on top of the flow equation, while here with proper time, we naturally are able to obtain the correct two-loop coefficient. So this is something I very quickly wanted to advertise. So now we have a technique, proper time flow equation. Let's talk, and very quickly, because everyone, I guess, in this virtual room know what asymptotic safety in quantum gravity is, but let's quickly talk about it. So the very simple idea is thinking of quantum gravity as a non-perturbative QFT up to arbitrarily high energies. So in a way, we want to generalize the concept of asymptotic freedom, which you see, for example, in QCD, where gauge couplings for high energy tends to zero. It has a fixed point at zero. And here we want to generalize it to the case of a non-zero value for the fixed point. And a famous example is Einstein-Hilbert gravity. So it was shown that at least, not at least, that the dimensionless version of the cosmological constant and the Newton constant have a ultraviolet fixed point. Now, this is interesting, but to make the theory really useful in a way, what we need to do is to find or to prove that it is predictive, that it can give predictions. And what this means, because we're doing non-perturbative physics, so now we have infinitely many operators in our truncation that we should consider, so what we want to do is to hope or to obtain or to prove that there is only a finite number of relevant couplings, relevant directions, and therefore only a finite number of experiments that is needed for the theory to be able to predict all the other infinitely many couplings that are therefore called irrelevant. And in Einstein-Hilbert, the way this looks like is that both G and lambda are relevant at the non-Gaussian fixed point. And the consensus in the community is, okay, that there are other relevant directions, but they are finite, and most likely all the many, infinitely many other directions are actually irrelevant. So despite there is not a proof, but we have an empirical realization of the asymptotic safety program. Now let's look at how this looks like for Einstein-Hilbert and the beta function for Einstein-Hilbert gravity. So here I want to introduce a bit of notation. So whenever I use a tilde on top of couplings, I mean the dimensionless versions. So here these are dimensionless cosmological constant and Newton coupling. And these numbers over here represent the matter content in the theory. So an S is the number of real scalar, the NV is the number of vector fields, and ND is the number of Dirac fermions. And importantly, this theory has a fixed point even if you remove the matter part, because of the cancellation of canonical and anomalous dimension contribution to the beta function. But once you start including matter in your theory, and you look, for example, at models like the Standard Model that has a lot of particles in it, then these objects here start driving the fixed point to bigger, let's say, values. And this is something that we will see later on in this presentation. Now here I had a blank space. What this is proper time. So the calculation of Einstein-Hilbert proper time in proper time for the full gravity part, so the anomalous dimension, was done in this work. And I think this was not presented over here. So let me quickly show you, at least for the sharp cutoff limit, the anomalous dimension they've computed. And what you see over here, or the things I want to stress, is that first of all, there are 5 different terms that come from the different sectors of the York decomposition. And secondly, there is a divergency in alpha equal 3. So from now on in the presentation, I will try to stay away from alpha equal 3 and look at values smaller than 3 for alpha, where alpha here is the graviton gauge fixing. And therefore, I will study only alpha between 0 and 2 or 2.5. And graphically, so this fixed point as a function of m, the regulating function, for no matter, so exactly the calculation done in this paper, look like this. So you see that the cosmological constant doesn't have much dependency on alpha, on the graviton gauge fixing, while g has quite some dependence, but it saturates very quickly, already around 10 or 12 for M, you see that it's already saturating to the sharp cutoff limit. So this is quite interesting. All right, so now what I want to do is to change a little bit the, okay. What I want to do is bring this idea of asymptotically safe quantum gravity into particle physics and quickly discuss the standard model at high energy. So there is a raised hand. I don't know. You want to speak up?
Hello, sorry for
Yes, of
interruption.
course.
Is what exactly is alpha again? Is it the gauge fixing parameter in the like in the
So
Lagrangian?
right, so this is the gauge fixing parameter for the graviton in the Donder harmonic gauge.
Okay, so you have your beta functions alpha dependent.
Yes.
Okay, it sounds a little weird to me, but okay, okay, thank
Well,
you.
all right. So this is okay. First of all, this is their result, but let me comment on that. So the situation over here is that obviously once you study the full theory of gravity, then you wouldn't expect to have gauge fixing dependency in your results, in your beta function, in your action anywhere. But here we're choosing a specific truncation. So obviously we do see some gauge fixing dependency. And
So this is an artifact of the
correct.
truncation, yes?
Very good. Yes. Yes.
And alpha equals 3 is where does it come from, this singularity? Is it also come? It also comes from the well, I mean, it's unphysical, right?
Yes, of course it has to be unphysical. I'm not exactly sure how it
Okay.
comes out from the calculation.
Okay. Sorry for
Yeah,
interruption.
no, no,
Thank
of
you.
course, of course, of course. Thank you for the question. Okay, so I was talking about standard model at high energy. So here I'm writing beta function for gauge couplings, and already I have in mind the standard model. So I have some coupling G1, which will be, for example, the hypercharge of the standard model, so an abelian gauge coupling. And then I have some non-abelian gauge couplings, like, for example, the SU2 coupling of the weak sector of the standard model, and the SU3 coupling of the color sector of the standard model. And when it comes to coefficients, here I'm keeping them free for a moment because I want to show you or to tell you that for the abelian coupling, this is always positive, is positive defined. Even if you have extra gauge groups in your theory, then once you diagonalize the gauge sector, you will always find one of them to be positive. So you always have one, at least, abelian gauge coupling that for very high energy, at least at one loop, runs into a Landau pole at some energy scale. And for the non-abelian gauge sector, so these two coefficients, can be positive or negative, but in the standard model, they are positive. Therefore, for very high energy, G2 and G3 tend to 0, and therefore we see asymptotic freedom. When it comes to the hypercharge, instead, like I was saying, we see a Landau pole, which of course is way above Planck scale, but it still is something, and we need to understand how to solve it. And there are, I guess, two main possibilities in the market. One is gut, so you could think that maybe some BSM physics could realize the gut at 10 to the 15 GeV better than the standard model does. But if you move a little bit to the right, then you hit Planck scale, and then you start seeing corrections coming from quantum gravity. And it might be that quantum gravity at Planck scale is able to change qualitatively the asymptotic behaviors of the gauge coupling, of the hypercharge specifically in the standard model. So now the question becomes, how does gravity influence this running? What are the diagrams? And there are these two diagrams. There is a tadpole and there is a sunset. And what is really important over here is that for every type of gauge coupling, this contribution is always looks like this. So the beta function of some coupling GI is proportional to the same coupling GI through a coefficient Fg, which depend entirely on the gravity sector, but that is universal. So it's the same for each and every coupling, for all of these guys. And very importantly, even in the Yukawa sector, we see exactly the same. So at least at leading order, obviously, we see that quantum gravity contributions to the Yukawa, to the running of the Yukawa couplings is universal, and this defines this coupling Fy. So now we have targets, Fg and Fy, and we want to compute them in some theory of quantum gravity, specifically in Einstein-Hilbert. So let me start with some literature, so FRG. So the first result was done over here by these people, and they computed Fg from the gauge propagator, so from the two-point function, using Wetterick equation. They worked with alpha and psi equal 1, where again alpha is the graviton gauge fixing, and psi here is the photon gauge fixing. And what they obtain is 3g over pi times some threshold function, which in optimized regulator is equal 1. Then there's been many more efforts actually to compute this Fg. For example, in this other work, they computed it using 3 and 4-point function and requiring that they coincide. And they worked in alpha equals 0 case, and once they impose the 3 and 4-point function are the same, then the result is also Xi, so photon gauge fixing independent. The single results depend on the photon gauge fixing, but the result once you impose the 3 and 4-point function are the same is photon gauge fixing independent. And this is what they obtain for Fg. So they have a dependency on the cosmological constant, and importantly, they have a suppression for high values of the cosmological constant. So, for example, if you study the standard model, we will see it later on, lambda at the fixed point is something like -3, -4, -5, and therefore this denominator becomes quite big, and Fg is suppressed. And then there's been another work from last year, which computed regulator and gauge fixing dependency of Fg, again with Wetterick equation. They study alpha and Xi equals 0. And here I want you to focus on the blue line, which is 100 times Fg for the standard model particle content. And the results they find, here I'm quoting 0.03, which is somewhere around here where you see this plateau, but okay, they vary really between 10 to minus 3 maybe, or 10 to minus 2, up to 0.03. And once we plug these numbers inside the standard model, I will show you later on, but let me quickly comment on this. This means, this will tell you that FRG favors asymptotic freedom for the hypercharge gauge coupling rather than asymptotic safety. So this is a little bit the result in FRG.
Sorry, what's on the
Yes.
x-axis there?
Ah, Sorry, thank you. So over here, they are showing the regulator dependency. So they're taking the exponential regulator, and in front of it, they're putting a number, this A with subscript E, and they are making this number vary. So this shows the regulator dependency within the exponential regulator, which
Okay,
in a
thanks.
way, I will not show it here, but in a way, this is actually consistent with the result that we find when we use the sharp cutoff regulator. So, and I don't know, maybe it's not really like this, but I would say that it's because both of them have exponential nature. But okay. Regarding Fy, I will not go too much into details because over there every different calculation has quite different Fy. So I will show only one result and discuss what it really what it tells us. So this is the result I will show, and here Fy is linear in G, and then it has a polynomial dependency on lambda, both in numerator and denominator. And what I want to discuss here is the sign of Fy. And it's the fact that for lambda smaller than around -3, Fy is positive, otherwise is negative. So what this means in this specific calculation, but this is quite a generic feature, is that at least at leading order, Fy or the sign of Fy is unclear. And then there's been a very nice result from last year that showed that even if you start with an Fy that at leading order for the standard model particle content is negative, once you include next to leading order in gravity, the Fy becomes positive. So, Manuel, please.
Hi, Daniele. Sorry to
Yeah,
interrupt
hi,
quickly. I
of
just
course.
wanted to ask a confusion about your alpha and psi choices, because in principle, there's, of course, three gauge fixing parameters, two gravity ones, typically alpha, beta, and then the photon one psi. Um, and you said that in the work from Astrid and Fleur, once they cry, psi drops out, but I'm pretty sure that psi always drops out of computations of FG because it's a linear gauge fixing and not a nonlinear one as in gravity. It's a linear uh,
So
gauge group.
So what I think, so I don't know, maybe I'm wrong, but I believe their 3 and 4 point function are xi dependent, and I think they show results in the paper with xi equal 0. I don't want to be wrong, but it might be for xi equal 0. But then they comment somewhere in the appendix saying that once you impose 3 and 4 point function to be the same, then it is xi independent.
Um, Not sure what is in their paper, but usually in all FG computations, the psi just drops out because it's an abelian gauge group. So, but yeah, for beta,
Right.
you're just working in harmonic one, I'm assuming here.
Yeah.
Okay.
Okay. Okay.
Sorry to interrupt.
No, no, of course, of course. All right, so going back here, the point is that we sort of expect, or the consensus now is that Fy is positive. And this is important because for me, because later we will see that in proper time, our Fy is going to be positive definite. So I will show you that we basically agree with this statement of Fy being positive with a calculation already done at leading order in gravity. Okay, so let me now start actually with the calculation that we've done in this work. So proper time calculations of Fg and Fy, and I will start with the setup where everything will become clear about the gauge fixing. So here, sorry, here is the Wilsonian action that we use, which is built from Einstein-Hilbert with the gauge fixing written over here, parameterized by alpha, which is the same alpha I've been using up until now. This is coupled to QED. So here you see the F squared term and the gauge fixing for the photon, parameterized with psi. And then there is the usual, not the usual, and then there is a Yukawa-like interaction over here. Now, we work using background field method, so we split fields into background and fluctuations, and we use the usual de Donder gauge. So this is the F mu that enters the graviton gauge fixing, and we have already chosen omega equal 1/2. So this is, please. There's a question.
Now, unmuted. Why don't you have a ghost term for QET?
Sorry again?
Why do you not have a ghost term?
Aha, yes. So this is something well known that the ghost is not going to give contribution to FG. So we know already that this is not going to enter the final result, so we just write it, but we don't need to compute it.
Didn't mean now the gravity ghost, I meant the QET ghost. If you are in a curved background, the Faddeev-Popov determinant becomes non-trivial.
Oh. So this is QED, right?
Yes, QED.
Um,
That the Faddeev-Popov determinant disentangles from the field is only true for abelian gauge theories in flat background.
Correct. But that's where I'm going. Very good. Okay, yes, thank you. Right. So we will work, okay, thank you for the assist. We will work in flat Euclidean background. Does that answer your question?
But is this sufficient for your study? Why do you avoid, for example, to use a curved background, for example, like a sphere?
Yeah, that's a very good point. So we had to start somewhere. This is the first time this calculation is done in proper time. So we decided as a very simple first step to use flat Euclidean background. But I agree with you, and it's in the list of things that should be done to also consider a sphere. Yes, yes, that's
Which even makes it somewhat easier because you simply can sum the eigenvalues to perform the trace.
okay.
Okay, it's only a side remark.
Yeah. Okay. Thank you. Yeah. Um, Okay, and final assumption or simplification is that we extract FG directly from the gauge propagator rather than 3 or 4 point functions. So if you want, in comparison to the results I was showing you before for the FRG, we are in the same scheme as the first paper by Daum and Reuter rather than in the second one. And why this makes our life easier is simply because then we don't need to charge our matter fields under abelian gauge symmetry. So in the computation of the Yukawa sector of Fy, we simply look at this term from the action and only this one. Okay, let's start now with the calculation of Fg, and let me remind you the flow equation. So what we have to do to compute Fg is to compute the Hessian, then diagonalize it, then we take the trace, we integrate in proper time, and then we will extract the coefficient of F squared, of F mu nu, F mu nu. So this is what we have to do. Here we have the Hessian, which is made of the infill space. So we have a graviton part and photon part. And this can be written in general like this, where in our flat background, minus box is going to become p squared. K is some non-trivial tensor structure. Then we have a potential term, U. And then we have a linear term in derivatives or in momenta, which comes from the off-diagonal part of this Hessian, from the mixed term. So basically, diagonalizing the Hessian simply means getting rid of this term in the middle. And because we want to use hit kernel, the other thing is canonicalize the box part. So just write it as minus box. So this is exactly the standard procedure that I want to describe here. So first of all, we multiply for the inverse of k. So we need to take the propagators for the photon and for the graviton, which here we keep generic in alpha and xi. And then we complete the square to remove this term, following a procedure by Jakiv, but okay, this is just completing the square over here. And this way, we obtain a Hessian that is block diagonal. It can be written simply like this, where the potential term or the shifted potential term looks like this. It has a first term omega, which comes from the initial potential u, now multiplied with the propagator. And then we have the term that came out from completing the square. So from here, y is v multiplied with the propagator, and this comes directly from having written the derivative directly in momenta. And if I want to look at this in a diagrammatic sense, then this second term is the sunset diagram that I was showing before, and this is the tadpole diagram. So now we have a Hessian that is diagonal, so we can take this trace, we can integrate in proper time, and we can extract the f squared coefficient, therefore obtaining indeed fg. And this is the result we obtain. Now a couple of comments. First of all, this is super simple from the point of view of the regulator structure. It's simply m over m minus 1. So for example, in sharp cutoff, when m tends to infinity, all this term just becomes 1. The graviton gauge fixing dependency just comes with this 1 plus alpha. And then the result is Xi independent. So we don't have dependency on the photon gauge fixing at the end of the calculation after we're taking it through the whole calculation. A couple more comments on this result. So first of all, it comes directly from the first term of the heat kernel and only from the photon part of the potential. So the graviton part of the potential is all higher order. At any order in heat kernel is always more than f squared. And then from the photon part of the potential, the first term is what you see here, and any other term is more than f squared. And the reason, or if you want another comment, but it's also the reason that there is only the first term, is that we don't have any dependency on the cosmological constant. There is absolutely no cosmological constant entering here. And therefore, not having the mixing between cosmological constant and f squared term in higher terms in the heat kernel does not generate more than the first term in the heat kernel. There is a question.
Yeah. What do you mean by the first term in the heat kernel? You mean like the first David coefficient?
Yes.
So
The quadratic, basically, what would be the quadratic divergency? So just the trace of this omega.
the
W.
quadratic divergence, not the logarithmic.
Yeah,
Okay. Okay, thanks.
of course.
The logarithmic is identically 0.
Yes.
In this method, the logarithmic is identically 0 because it doesn't mix. So the logarithmic divergence would mix the Newton's constant and lambda and the cosmological constant, but since they belong to different diagonal blocks in the heat kernel, they do not mix. So at all orders in the heat kernels, at this level of the calculation, there is no logarithmic divergence. There's only quadratic.
Okay. Thank you.
And the reason why we don't see cosmological constant terms is because they cancel in the sum of these two terms. So singularly, they do have some dependence on the cosmological constant, but then when you consider the sum, it cancels out. And because we don't have cosmological constant or higher order in the heat kernel, we also don't see any sort of suppression. So like in the result by Astrid in FRG, we were seeing some polynomial suppression in the cosmological constant. Here, we don't see any of that, either polynomial or exponential, any sort of suppression with lambda. Now let's go to Fy, the calculation of Fy. So here is the Hessian. We have a graviton part, we have a fermion part, we have a scalar part. And here, this Hessian is extremely simple. Let me even show you the potential. It simply looks like this. You have cosmological constant plus a term proportional to the Yukawa and to the Yukawa operator times some tensor O. So basically, diagonalizing the Hessian is the same as diagonalizing this guy. And the way you do it is by splitting it into traceless and trace part with the corresponding eigenvalues, and then the trace can simply be taken because this simply becomes the dimension of the traceless part of this tensor, which is 9, times the exponential of the eigenvalue times this object over here, and then the same for the other eigenvalue, which in the trace sector has, and the trace sector has dimension 1. So then you expand the exponential to take the linear term in the Yukawa operator, and this way you obtain Fy, which is given by these two terms. And here you see that because m is by definition bigger than 2, so 3 and above, then this exponent is negative. And therefore here we see a polynomial suppression with the cosmological constant. And when we take the limit m going to infinity, so the sharp cutoff limit, this polynomial suppression even becomes exponential. So here we see that for negative and big values of lambda, we do have a suppression in for Fy. Also, as you can see from here, this is always positive. So this Fy at leading order in gravity in proper time is always positive, is positive defined, which is also a quite nice feature. Here in this plot, I'm showing Fy as a function of the regulator m for g equal 1. Up here, these first two lines up here are for the cosmological constant equal 0 and two choices of the graviton gauge fixing. And then down here, you have the cosmological constant equal -4 for the same choices of the gauge fixing. So basically, you see that you see in action the suppression. So you go from order 1 for Fy to 10 to -1, 10 to -2. So we start seeing this suppression in action. So now we have calculations for Fg and Fy. And what we can do is plug this into some theory with matter and try to see what are the results that we obtain. So the simplest model is minimal matter model. And let me start by reminding you actually the results we have obtained. So here you have Fg for generic m and the sharp cutoff case, and then Fy and the sharp cutoff case. Actually, incidentally, let me also comment on this. I forgot before. Fg, once we set alpha equal 1, which was the result by Daum and others, we get exactly the result for lithium regulator. So in a way, so what I'm trying to say here is that our sharp cutoff regulator is the same as the lithium regulator result that they obtain, at least for this calculation of Fg. Now, speaking about minimal matter, so here minimal matter means all of these numbers equal 1. And then in all plots, I'm showing you in solid blue the sharp cutoff, and in dash red m equal 3. On the x-axis, you have always alpha. And then up here is g and lambda computed by the group in Catania, but this time with all the numbers equal 1, so with matter. And what you see is that, exactly like I was explaining before, once you approach the divergency at 3, you start seeing some dependency on lambda, on the cosmological constant, that becomes quite strong and therefore most likely unphysical. But as long as we stay far away from there, so 1.5, 1.6, then the results, it's quite, I would say, is gauge fixing independent, or at least it doesn't have a strong gauge fixing dependency. Also notice that both g and lambda in this model are positive, small, so smaller than 1, but both of them positive. So over here, instead of having a cosmological constant suppression for Fy, we will have an enhancement. And indeed, we see that Fy gets value of 1, 1.5, so quite big values. While for Fg, which does not depend on lambda, it depends only on the Newton constant. Because the Newton constant is order 0.5, 0.6, then Fg is order 0.5, 0.6. So, please.
So am I understanding this correctly? Like in the perfect world, we wouldn't get any dependence neither on alpha nor on m, which is the regulator parameter.
Correct.
So, like there is this minimal regulator dependence, and similarly, you want the dependence on alpha as low as possible. So you choose to say that the physical value is somewhere around the maximum or the minimum, right?
Yeah, so we
In
haven't done
both
this.
in both variables, alpha and m, right?
Right, we haven't done this sort of studies. This is something that in the FRG study that I showed before with the plot in the bottom right corner, they have done using the principle of minimal sensitivity to fix this gauge fixing parameter. We haven't done it over here. Here we just show different values of the cutoff, and here we are choosing the extrema, so m equal 3 and m equal infinity, and then we are varying alpha. Well, you see it over here between 0 and
Okay,
2.5,
okay, thanks.
of course. Okay, now moving to the standard model, and maybe I should also move a bit faster. The standard model has many more particles or many more fields. So here you have an S and D and V. And because of that, already the gravity part is completely different. So G and lambda are completely different with respect to the minimal matter part. So for the Newton constant, we see that the fixed point value varies between 4 and 3, 2, anyway, is quite large. And for the cosmological constant, this is negative and also quite large, -6, -5, -3, and so on. And this is something we see immediately in Fy. So we have a very strong suppression once we study the sharp cutoff, because obviously here the suppression is exponential, while over here is polynomial and also m equal 3. So it's this object to -2. While for Fg, once again, because it depends only on Newton constant, and Newton constant has this swing over here, then also Fg has quite some swing, so it does have a bigger dependency on the regulator and on the gauge fixing, on the gravity on gauge fixing. Okay, so now we have a calculation of Fg and Fy. We have some sense of how they vary in different models of particle physics. So the next question that I want to ask and sort of answer is, what are the phenomenological implications of this calculation of Fg and Fy in proper time? And to do so, I will talk very quickly about the heuristic approach to asymptotically safe quantum gravity. So here the idea is to take Fg and Fy not from a specific theory of gravity, but to just keep them as free parameters and fix them through the experiment. So the idea is, if I have a theory which below Planck scale has some beta function computed, for example, in perturbation theory, then we know already above Planck scale, they get corrected this way with Fg and Fy. But these objects now are fixed by the low energy data, so if you want, by experiments for the standard model, and by the assumption of a fixed point. So now, since we have the assumption of a fixed point, we can compute the critical exponents, and we will have relevant and irrelevant directions. And for phenomenology, relevant direction means that this is a free parameter of the theory. We can choose it to be whatever we want, for example, to match low energy data. And an irrelevant coupling is a prediction of the of asymptotic safety. And importantly, what we want, of course, is as many parameters as possible to be irrelevant. So we would like to have them all irrelevant. Of course, this is not possible, so we wish to have relevant parameters only that we know from experiments, so only for the standard model sector, and then all BSM couplings to be irrelevant. So this is a little bit the gist of it. And let me give you a very quick example, or yes. So say you have a theory which is only gauge sector. For example, you have a standard model part, for example, the hypercharge, and then you have some BSM part, that with a gauge coupling that you don't know. And if they're both abelian sectors, then they might even mix. So you can have a kinetic mixing. And now the idea is the following. The hypercharge, we know it at the LHC scale in the deep infrared. So we can take this value as a boundary condition, run it up to Planck scale, and then here we assume that there is such a fixed point, and therefore we extract Fg from assuming such a fixed point for the hypercharge. Then we can plug Fg into the fixed point value for the two BSM couplings that we don't know and that we wish to know. This will set a boundary condition at Planck scale, so in the UV. And therefore, we can run the beta function down to the infrared, to the LHC scale, therefore obtaining predictions for both of these BSM couplings. So basically, by using the universality of G, fundamental, and the assumption of a fixed point, we are able to get unique predictions of two BSM couplings. Now, this is the the best case scenario, and what I want to do in the next and last slide is show you whether this works or not in different models, in the standard model and in some BSM models as well, in the calculation that we have done with proper time. So, in this table, I'm showing you the standard model, B minus cell extension of the standard model, and a SU6 GAT model. And I'm showing you here for different values of Fg and Fy, the predictions that we would get from such values. So for example, in the B minus L model, for this value of Fg, we would have both the hypercharge and the BSM gauge couplings to be safe, so to have an interactive fixed point. While for this range of value, we would have the hypercharge to be Gaussian relevant, so free in this table. But the BSM couplings still interactive, still predicted by the fixed point, by the asymptotic safety, if you like. Why these models are interesting from phenomenological point of view, let me quickly comment on that. So for the B-L model, it was shown that through asymptotic safety, it is possible to dynamically generate the mass of the neutrinos in the model. So this is a model that in the Yukawa sector has some BSM neutrinos. And through asymptotic safety, thanks to asymptotic safety, you can generate the small masses of such neutrinos. And on top of that, it also has some potential for gravitational waves signature. Regarding the SU6 GAT model instead, this still through asymptotic safety shows emergence of dark matter. So here we have a potential for testing predictions coming from models with asymptotic safety to test them at colliders or anyway with gravitational waves. So this is really interesting from the model building point of view. But now let's look at what values of Fg and Fy we obtain from our proper time calculation. So here I'm going to show you isocontours, and I will work for alpha equals 0 in both cases and in the sharp cutoff case. So here you see different values of Fg are different lines, and the same for Fy. Let's start from Fg. So you see that this line is Fg equal 2. So for both the standard model and B-L model, Fg is quite large, which is something that we have seen already before in the slide about the standard model. And therefore, this Fg is too big to generate an infrared fixed point, which would need to be these values. And therefore, our calculation in proper time favors asymptotic freedom rather than asymptotic safety, basically confirming the result from FRG, or agreeing, to better say, with the result from FRG. On the other hand, when it comes to the Yukawa sector, we see that this blue line over here is 0.001, and the fixed point for the B-L model, this one is 0.02. So we are extremely close. I don't think it's exactly the same number, but it's anyway very, very close. So you could expect that with truncation dependency or gauge fixing dependency, regulator dependency, you can obtain the value of the fixed point. What this is to say that our Fy calculation is compatible with the assumption of an interacting fixed point. About the standard model, this is a little bit less clear, I would say. Here, this value is 0.01. So actually, we have a value for Fy for the standard model particle content that is a little bit too big. It would have to be around 10 minus 3, 10 to minus 4 for have either this type of fixed points. But anyway, I would expect that once you include more rich truncation, then it might be that actually this value starts to get closer to this line over here. Okay, so with this I will go with my conclusions. So the running of gauge and Yukawa couplings in the standard model and simple extensions is well described perturbatively up to Planck scale, where quantum gravity contributions must be considered. At leading order, these are linear in the couplings through universal coefficients that we have called Fg and Fy. And from Wetterich equation, we know that Fg is positive, while Fy, or the sign of Fy, is unclear at leading order and then positive at next to leading order. So we have computed for the very first time Fg and Fy in proper time renormalization flow within the simple Einstein-Hilbert truncation, and we've studied, importantly, gauge fixing and regulator dependency. We see that Fg is order 1. There is no dependency on the cosmological constant because the whole result comes from the first coefficient of the heat kernel. Fg is also photon gauge fixing dependent, which is also important for the consistency of the proper time flow. Fy is always positive and is always cosmological constant suppressed, so that values interesting for phenomenologies are accessible within leading order in our calculation. And then we see that for both Fg and Fy, there is a small dependency for minimal matter content, so for few particles, while for many particles, like for example the standard model, the dependency becomes much more relevant. Comparing our results to phenomenological studies, proper time favors asymptotic safety, like in the FRG, for the abelian gauge coupling of the standard model, while fixed point of the Yukawa sectors are accessible and, I guess, should be studied in a richer truncation of gravity. Thank you.
All right, thank you very much, Daniele, for the nice talk.